So now let's look at imprint system. So the most obvious system is the parallel plate. We can use the parallel plate. And this is the obvious one. So you have the top plate, you have bottom plate, you have the wafer here, and you have your mold. So this one, you have the so you apply the pressure here. This is called a solid state parallel plate imprint. This is one most obvious. So I will not talk about this one. So first we talk about the air cushion press. This is called air cushion press. So what's the point for this? How to do this? So here you put the mold onto the substrate, then you pump the air out. Then you apply then you fill in the gas, high pressure gas. This will get the pressure. So here is the indicator of this called a pressure indicating papers. So there are a lot of liquid capsule inside this paper. So when you apply the pressure, those capsules will be broken, then it will release the color. The uniform color here. So the uniform color here shows that you get very uniform pressure. So when you do the gas pressure imprint, you get much more uniform pressure than the solid state press. This solid state press is the same thing as what the parallel plate press. It gives you better pressure uniformity. So this work was first done by the company called Nanonex. So the company Nanonex still exists today, and it sells the nanoimprint machines. So the idea is that you have the bottom plate. So you have the bottom plate, then you put your wafer here, and you put your mold. Then you have the plastic sheet. So this white color here. So this white color is this plastic sheet. So this sheet, so you pump out the air. Then because the air pressure from outside, you push it. So no more air will come in. So when you apply the gas pressure, the air will not be coming in. So again, so this one gives you the very uniform pressure. But normally, if you do the parallel plate, you can also get okay pressure if you put something soft like a paper, or you put a paper or something soft between on top of the mold and below the wafer. This way you also get okay pressure uniformity. So you don't have to use the air press. But this one obviously gives you the ultimate pressure uniformity. So when we have the air press, so we can even do the imprint on the curved surface, as you see here. So this one is the macro scale structures imprinted by the air press imprint. You get a very uniform pressure, uniform pattern. So this is called a roller nanoimprint lithography. Roller nanoimprint. So there are two ways to do this. The first one, you have the mold. Surrounded this roller. Then you roll this mold along the surface. You put this one on the hot plate. You heat it up. So this PMA is obviously this for the thermal imprint. Another way to do the roller imprint is that you put the mold onto the PMA, then you roll this roller to give the pressure. So you heat it up, you give the pressure, then you do the imprint. This one is also PMA. It is also a thermal imprint. But this work was published in 1998 by my personal colleague Tan. So we are in the same group. You see, this journal here is not a very top journal. But back then, we don't see too much profit for this work. But actually, very recently, I talked to a few companies making the imprinter machines. But they said actually they use this process to do their imprint it is used for the mass production. That's why I bring back this slide here. So the difference here in the first paper we use the thermal imprint, but nowadays for the mass production we know thermal imprint you need a very high pressure, long time, so it's complicated. But for the mass production, the people use the UV imprint. So first you use the roller to make the contact. Then you take away the roller, then shine the UV light. This way you can have very large area imprint. So the companies who make the liquid crystal displays, they use this kind of imprint. They make the polarizer for the displays. So we'll look at how to make the polarizer, how does the polarizer work later on. But there's another way to do this is also a kind of roller imprint. But the difference, this one is called a roll-to-roll imprint. So here we have the mold, we have the wafer, this is solid, this is rigid. But in this case, we have a roll, a plastic web. The plastic web come here and come here. This is the place that you apply the resist. This is rotating, so you have the resist coated on the web. We have this a plate, razor plate. This razor plate will remove the excess coating. Then it passes to here, and you have the mold here. You have the mold here. You do the either heating or UV curing, so you can do thermal or UV imprint lithography. Afterwards, you get the pattern here. Here you get the example for the polarizer. It's called the wire grid polarizer. So you can check wire grid polarizer in the Wikipedia. I will also talk a little bit about it later on. That means so you have the grating structure. Then you coat. You do this is the metal evaporator. You coat the metal. You have something like this. Then this is a very easy and cheap way to make large area polarizers. This roll can also be used to make other devices for the large area electronics like display, optical devices, and on the flexible substrate. But obviously, this is a very cheap and high speed way to do the imprint. So the mold here, this mold here, it contains of 3 layers. So we have the PET. This is the substrate. PET is a kind of a plastic foil, a few tens of micrometer. Then we have the double-sided tape. Then we have this ETFE mold. So we have seen this material before. So now I will show you what is the ETFE mold. Yeah. So this one. This is the ethylene tetrafluoroethylene. This is the ETFE mold. This is the material for the ETFE mold. If you have the fluorocarbon, this gives you the low surface energy of the mold. So here are the images done by the roll-to-roll imprint. So the A and B is done by the thermal roll-to-roll mold using the PDMS grating. The PDMS mold imprinted into the PET strap. So CDE, this one is done by the UV roll-to-roll imprint. In this case, the mold is made of the epoxy silicone grating pattern imprinted into the PET mold, PET strap. So the pattern area, the grating area here is a 700 nanometer pitch. You see it's colorful. We will see later on why it will be colorful. So this is called a roll-to-roll imprint, give you a very high throughput. Next example is called electrical field assisted imprint. Electrical field assisted imprint. The idea is very straightforward. And you do that when you apply. We have the parallel plate. This is the parallel plate. If you apply a voltage, then there will be positive charge on this side, negative charge on the other side. Then you get the force. You have the electrostatic force. You bring this thing try to come together. This electrostatic force give you the force needed to do the imprint. This is called electrical field assisted imprint lithography. Now here's the setup. So first you have the substrate silicon. Then you have this underlayer. So we know that when we do the UV imprint lithography, there are 2 layers. Well, this underlayer, that is the polymer, like a PMMA or ARC, anti-reflection coating polymer layer. Then we have the top layer. This one is the UV curable resist. Then we have oxide. This is the mold. Then we have ITO. So what is ITO? ITO is the indium tin oxide. But this one is conducting and transparent. So we know that. So normally a material is if it is very transparent, like the glass. So glass is very transparent, but it is insulating. If it is very conducting, like metal, the metal is very conducting, but it is opaque. So this material here, ITO, it is conducting and also it is transparent. It obviously is not as conductive as this one, indium tin oxide will not be as conductive as the pure metal, but it is still conducting enough. So we need the conduction to make the electrical contact, and we need it to be transparent, so that we can shine the UV light. How much field we need? So the field we need from here, we need 1 atmosphere pressure. So we know that for the UV imprint lithography, the mold will wet the resist. As a result, we do not need high pressure. So the resist will fill in the mold cavity by the capillary force. But still, we need some pressure to make sure the mold and the wafer is in good contact. So this one we need 5 times 10 to the power 5 volts per centimeter. That is 50 volts per micrometer. So here is the formula here. So here is the formula pressure we get for a given voltage. So the separation, the distance here, the separation and the voltage. If we know the voltage and the separation, we can calculate how much pressure we get. And this one I will show you how to derive this formula. But here we assume epsilon r equals to 1. We assume this one equals to 1. So that means this is the case for iron. But if we have epsilon r not equal to 1, we can do the same derivation. So the idea is like this. So we have the applied voltage. We have the charge here. So the force is the same as the force from just the force from the charge. So the voltage is not the voltage is just to generate the charge. So now we will look at what is the attractive force between the positive charge and negative charge. This give you the pressure value. So I have done this previously. You can see here. So we have the parallel plate, positive charge on this side, negative charge on this side. This one is the plus Q. This one is minus Q. We define the charge density. So charge density is given by Q, the total charge divided by the area. The area is the area of this plate. So now we need to find out the pressure. So the pressure given by force divided by the area. So we want to know how much force exerted by this plate onto this plate. Then we need to know what is the electrical field. E field from this plate onto this plate. So we need to know this value. How big is the electrical field from this plate onto this plate? And the electrical field can be calculated using it's called a Gauss law. So we can use the Gauss law to calculate the electrical field. So the Gauss law says that for any enclosed area, so the E dot S, this is the area. E is the electrical field equal to the charge enclosed in this area divided by epsilon 0. This is the Gauss law. I know you learned this thing in your second year. So from here we can know that. So now we take this area as an example. We consider this area here. This volume, actually is a volume. We consider this volume here. And we have the E field to the left side, E field to the right side, no E field this direction or E field this direction. So on the left side it is equal to E this area, this area. So we have totally 2 times electrical field times this area and this area. This one equal to Q over epsilon 0. So the charge inside is considered as Q. So we have Q over epsilon 0. So this Q, this charge divided by this area, so this charge divided by this area equal to sigma, which is the charge density. So you have the E equal to sigma divided by 2 times epsilon 0. So this is the electrical field from this plate exerted onto this plate. Then the pressure is given by force divided by area. So the force is equal to field times the charge. So here is this negative charge here, times the field divided by the area. So the charge by field divided by field equal to charge divided by field equal to the sigma. So in the end, then you put the electrical field from here. You put this one to here, you get sigma squared over 2 times epsilon 0. And this is the pressure. So now we need to find out what is the charge density. So we know that for the capacitor, the charge equal to capacitance times the voltage. For the parallel plate capacitor, the capacitance, this term equal to epsilon 0 S divided D over V. Then the Q over S, you bring this S to the left side, so you get the sigma again. The sigma equal to epsilon 0 V divided by D. So epsilon 0 V divided by D, because you put the S to the left side. Then you put this sigma, you put this sigma value into here. So you will get this formula for the case of epsilon R equal to 1. If epsilon R is not equal to 1, all the calculation is the same, but this term here, there will be epsilon R term here. There will be epsilon R term here. If epsilon R, this C will be different. You have epsilon R here. So here is the electrical field associated imprint. So time 0.65 seconds, propagate from this corner to the right corner, so you get the imprint. You can see you get very uniform imprint. But in reality, this process is very nice. It's published in a very good paper, but it is not much practical value, because you need to quote ITO. you need to apply the voltage. It's complicated. If you do a regular UV imprint using the mechanical force, the mechanical force UV imprint is much simpler than the electrical field assisted imprint. So as a result, this is why just to show that so this thing works, but it's not really useful. So now we look at imprint applications for the nanoimprint lithography. So the first application is the electronics. This is the single electron memory with 8 nanometer dot using nanoimprint lithography. So what is the memory? So memory, we know that so we have a flash drive. We have flash memory. We also call it USB drive. So SD card is the same thing. So how to make the nowadays there is another name called the solid state. Solid state drive, hard drive. So it's the same thing. So solid state hard drive, flash memory, SD card, USB drive, they all have the similar recording mechanism. So what do you do? So normally we know that for the casing of the MOSFET, you know about MOSFET. You have here, you have the insulating layer here, you have the conducting layer here, and you have this gate voltage. This is the insulating here, and conducting here, and here is the source, here is the drain. This is the MOSFET structure, right? This is MOSFET structure. Your conducting layer, conducting, this is the gate, this is the connecting the gate. Your source drain, you have the insulating here. So for the memory, we do something on this in this insulating layer here. So what do we do? So we add another layer here. So we have another layer here. Sorry. So this layer here is, can be a silicon. This layer here can be amorphous silicon. So this is why it's connecting. So you have the channel here, insulating here, connecting layer here, insulating here, another connecting layer for the gate. So if we have a positive voltage, if we have the positive voltage, we apply a voltage, so the charge here, electrons, or maybe holes, electron or hole. So they may tunnel through this barrier to come to here, right? So the charge, we apply a positive voltage, so the electron, negative charge, will be attracted. It may come to here, it may come to this layer. So we have actual charge into this layer here, then the threshold voltage, VTH, will be modified. So this is the threshold voltage. When we have the charge trapped in this area here, the threshold voltage will be modified. This way, this can be detected. So you have charge here, or you have no charge here. When you have charge here, it's 1, state 1. When there is no charge in this layer, it's state 0. So how to get rid of the charge? If you apply a negative voltage, when you apply a negative voltage, the electron will be pushed back. Then you get rid of the charge. This is the region. So how many charge is needed to change the threshold voltage? This depends on the area. If this one is really small, if this area here is very small, you can see it is so small, it's only like a small dot, very small dot. Then even though you have only 1 electron, you have this is the threshold voltage, this term here. So this one will change. So we have 1 electron here, 2 electron, 3 electron. So this is you have 1 electron here, 2 electron here, or 3 electron here. You see the different threshold voltage. This way you do the memory process. So this effectively it detects whether you have charge here or no. When you have charge here, is 1. When you have no charge, it's 0. The problem is that, so for this one to work for the room temperature, this one needs to be very, very small. For single electron, you have to be very small. So it's difficult to do it by electron beam lithography. So what you can do here, first, you use electron beam lithography. You use electron beam lithography to make a mold. So what's the mold? So once the mold is made, you can copy it by your imprint. This is the idea. But in reality, we know this is not successful because when you do the imprint, you have the alignment is very difficult. It's very difficult to do alignment, and also you have the defect. You have touched the particles defect. So this is just demonstration and no commercial value. This work is done by the HP, so it's all done by imprint. It's flexible, ultra thin display. You can see it really, looks like very, very good. You can make it very cheap, a large area, very efficient. But in reality, this is so complicated. It is very complicated. So the researcher the researcher from HP, who is responsible for this project, he came to University of Waterloo to give a talk maybe 3 or 4 years ago. He talked about this process. So because for imprint, we know that alignment is very difficult. It's very difficult to do alignment. If you do the row to row imprint, alignment is almost impossible. And what he did, his group did, he made the mold something like this. So you see, the mold contains multiple layers of the structure. For example, this layer is for the source, this layer for the source drain, this layer for the gate, this layer for the metal connection. So they have all the layers. They have all the layers embedded into one single mold. Then they do the imprint. Then follow the very complicated pattern transfer process from the mold resist into the amorphous silicon. So eventually they can make the display. So this is very great work, but as I said, it's too complicated to be commercially useful. So Nanoimprint is more useful for optics. It's called sub-wavelength optical element. For the visible light, the wavelength is a few hundred nanometers. So we can make easily, the feature set smaller than the wavelength. Then there will be many new different functions. For example, we can make anti-reflection surface. We will talk about this later on. A wave plate. This is the wave plate. So we know that for the artificial birefringence, we know about for the birefringence. So what we have, the refractive index along one direction is different from the refractive index along another direction. But the direction is relative to a certain crystal orientation. This is called birefringence. So we need a single crystal material to do the birefringence. So here, this is the kind of artificial birefringence. We have the grating structure here. The index, if the light is polarized this direction, or if the light is polarized this direction, if the light is polarized perpendicular to the grating structure, or if the light is polarized along the grating direction, but they have they are not the same. So this is the birefringence, right? Birefringence. Different polarization give you different refractive index. This is called wave plate. Then there is the polarizer. We see polarizer later on. So filter. Other grating structures here, naturally they are filter. Add drop channels. This one can be done using the polarizer and the wave plate. So optical couplers, lenses, zoom plate, photonic crystals, a photodetector, laser, and many things more. So here we have talked about the zoom plate. This is the zoom plate. Zoom plate of 70 nanometer minimum feature size. The problem for the zoom plate is because of this. We know that R, N, lambda, F. So we have seen this formula here. So for the fixed zoom plate, you can see lambda is inversely proportional to F. So longer wavelengths will be focused to shorter distance. So shorter wavelengths will be focused to longer distance. This way, different wavelengths, different color of the light will be focused at different place. This is not good. This one, the pattern very simple. You just have the circular patterns. But you can design something like this. This is called a meta lens. At the moment, this is a very hot research topic. You can see the paper published Nature Nanotechnology and Nature Nanotechnology. This is very top. This is the very, very top journal for the nanotechnology. This is 2 years ago. This is 1 year ago. So what is the meta lens? For this one, have the circular pattern. So in this one, each of the building block, the pixel, each of the pixel is designed differently. So each of the pixel is designed differently. So you modify the face. So when the light come out, or when the light when the light comes from this side to the other side. So the phase will be modified on each of the pixels by a very, very complicated design work. So you can design the block orientation, thickness, the sizes, so that you can see all the different color of the light, they are focused at the same spot. This one, different wavelengths, different focal loss. This one, different wavelengths, the same focal loss. This will be very useful. For example, if you put this one in the camera, so the camera will be very, very small, lightweight, very thin and lightweight. So we have a Waterloo, a graduate student. He started a company in California using a methodless. What does his company do? They do with the it's called endoscope. This is a product of this company, endoscope. That means we have this. So what is endoscope? So those are the endoscope. For example, you can put the endoscope into the human body, into the ear to look inside the human body. So in this case, his product endoscope, he used the methodless. As the less at the end of this endoscope. This one you can see very small and very efficient to focus different colors. This is the ideal case for the endoscope. So his company want to detect the lung cancer. To detect the lung cancer, you need to know the lung cancer when they are like a few hundred micrometer size. So it's very hard to see by other lasers. But by this kind of lasers, you can see 100 micrometer size. This is the early stage of the lung cancer. But this is the anti-reflection. So here, this one, anti-reflective surface. This is also called a moth eye structure. Why it is called moth eye? You can see this is the moth. You can see the eye is very black. It is black because it has this kind of nano structure. You can see it's very black. When the eye is black, this will prevent it to attract its predator. It's for the safety of the moth. So the predator will not see it. We have a very black eye. So this is different from the cat. At night time, the cat's eye is very shiny. So why it is black? So it is black because there is no reflection. The light comes in, no anti-reflection, no reflection, then it will appear black. So we know that for the normally when we have the interface, like this. So here you have the like n equal to 1, n equal to n. So when the light comes in, you have the reflection. This is the reflected light, this is R. So the reflection is given by this formula here. This is the reflection of the intensity n minus 1 square, n minus 1 divided by n plus 1 square. This number, if the n is 1.5, you see it's not so big. But we have the other, this is for the normal incidence. If the light comes in this way, if the light is, we have the glancing incident, then the reflection will be very, very high. This is not good for many applications. How to reduce reflection? This is done by this kind of nanostructure, because this is the nanostructure you have here. So basically, what we care about is called effective reflective index. Here you have structure like this. Here is the substrate, but n equal to 1 equal to. You can imagine, okay, at this point here, n is very close to 1. So here maybe n equal to 1.2. So right, 7. So this one n equal to say 1.5. So here maybe here n equal to 1.3. So those, so you have the gradual change. You have the effective index gradually change from 1 to 1.5. This way you get very low reflection. This is the idea of anti-reflection. Otherwise, if you have abrupt increase, you have this kind of abrupt interface, then you get high reflection. So here's the polarizer. So this example here, the polarizer. So you can see here. So when the light, this is what is easy to fabricate. You have the grating in the PMA. Then you coat the metal. So this same idea as this work here. Right? This This one is also, you have the greasing structure here, then you coat the metal. Very easy to make large area polarizer. So when the light come in, we have the one light, this TM, this is called TM mode. So the polarization is perpendicular to the line. Another one is polarization parallel to the line. You can see in this case, the TM mode has high reflection, TE mode has low reflection. At this particular wavelength, the ratio of the TE and TM and over T is more than 200. So this is called a polarizer. So that means in this case, so the TM light will be reflected, T light will not be reflected. So which one is reflected depends on the metal thickness and also the metal material and the weight. So you can design differently. If you design differently, you can have the opposite case. So here we have the metal on the bottom. So we have the metal on here. If we can remove the metal here, if there's no metal here, then the light can pass through. And then you have the transmission polarizer. This one is the reflection polarizer. And no metal here, you get transmission polarizer. So this is the idea for the company called non-opto. Called non-opto. So this company is also a spin-off company from Princeton University. But they got 40 million. They got $40 million investment. They make a good, very, very good product. But in the end, after a few years, this one is not very successful because there are other cheaper ways to make the polarizer. So how to make the cheap polarizer? So you have the not polarizer, it's PVA, I think. Polyvinyl alcohol or polyvinyl acetate. You have this polymer here. You put a lot of iodine. You put this element, iodine, in the polymer. Then so you stretch it. You stretch. So when you stretch it, it become, this iodine will be elongated along a certain direction. Then it become a polarizer. You can see that this stretch it is so cheap to make. But this is why you need lithography and metal deposition. That's why this company was not successful even after $40 million investment. This one is very popular at the moment. It's called diffractive optical element. So I think this will be the major application for the nanoimprint lithography. Now here's one example. In this example, you have looks like a very random pattern. You get random. You see the pattern here is very random. Actually, inside this random pattern, you have this word embedded in the random pattern. When you shine the light to this word, the word will shine up. You can also have this, this image. This image can also be embedded in this kind of random pattern, so it will show up. This is another example of it's called DOE, very popular term, diffractive optical element. You shine the laser light, you can modify the laser light, then you modify the wave front. This is the diffracted light. You design many complicated patterns here. You get this wave front. Wave front. Then it can be line array, a dot array, a random lines, or mesh, depending on how you design this pattern here. So one of the applications for this is for the face recognition to unlock a cell phone. For example, we have this 2D dot array. So when it come out, it become a 2D dot array. So there's lots to shine onto the face. The different areas they come back to the camera. So then the pattern after come back to the camera, so the pattern, the intensity and the position will be different. Each person has a unique pattern. This way you can do the unlock of the cell phone. The advantage for this one is that this one sees the 3D pattern of the face. Otherwise, if it sees only the 2D pattern of the face, you can put a photo. You can put a photo to unlock a phone. But here it's 3D. You have 2D dot to shine onto the light, then come back. It's really kind of 3D pattern. 3D information will be guided. But this is also very popular application. Many companies they are working on this. This is called AR, augmented reality. For the AR, you need to guide the light. You need to guide the light from here to here. So how to guide the light? So this is how to guide the light. To bend and guide the light propagation. So we have the grating here. The light comes in, diffraction on the left side to the right side, and you have this. This is the 0 order diffraction. This is the -1 order. This is the +1 order. This is for the normal grating. So when the grating got slanted, it's called a slanted grating. So we have the grating like this. Most light, 80% of the light will be diffracted to the left side. So no to the right side, and very little 0 order diffraction. This way the light come here, maybe bended, maybe guided through this one. We got light come here, then guided through this waveguide. Then it will be used for the AR lens. So how to etch this slanted grating? So the normal RE will not work. So for the normal RE, so you may think, you have the plasma here. You have the top plate, bottom plate. You apply a radio frequency. This is the radio frequency. This is the normal RE. So you may think we put the sample, we have the mask here. It will tell the sample the etching may be slanted etching. But actually this will not work because we have the wafer inside the plasma. It will be negatively charged because electron move faster in negative charge. Then the field is still this direction. Electron field is still this direction. The ions like the fluorine argon, they come here vertically. Then still perpendicular to the wafer surface. So the etching will be perpendicular to the wafer surface. Then you get something. You get this vertical etching. You get rather than slanted etching. To do the slanted etching, we need to use the ion beam. So if the ion beam come here, argon ion. If the ion beam come here, then you get this slanted etching. But for the ion beam etching, we have very poor selectivity. So the etching rate of the mask is the same as the etching rate of this material here, which is the silicon oxide. It's the same. So to get the selectivity, to get high selectivity etching, we use reactive ion beam etching. It's called reactive ion beam etching. What do we do? We have this CF4 gas. This CF4 gas will form ions. They will form CFX ions. So this CFX ions will go this way, then it will etch the silicon oxide faster than the mode, which is usually it is chromium. So here what I wrote here is the CF4 added to argon, but actually this may not be the case. So I prepared a slide maybe 2 weeks ago, but recently I'm studying RBE because a company asked me to make this kind of structures. So I'm reading about RBE. So it looks to me you do not need argon. You don't need argon. You just fill in CF4 gas. You do the etching, no argon. But this is also another very, very successful application for the nanoimprint lithography. It's called micro metal match for the TCF, transparent conducting film. So we have seen before that. So normally for the transparent conducting film, so we use ITO, indium tin oxide. But the indium tin oxide, the resistivity is not low enough for the large area. So for the large area display, we need higher conductivity than ITO. This is again indium tin oxide. So the solution is to make a metal mesh, because this is the metal mesh. You can see that. So first, we have the metal. So when we have the metal, it will be conducting. So it will be connecting. Then we have the mesh. So here the light can go through here. So the light can go through the mesh. Then it will be transparent. So it is transparent and conducting. So how to make this metal mesh structure? Here is the process. First, we do the photolithography to pattern the photoresist. Then we do the nickel electroplating to copy the mold onto the nickel. Then we put the nickel mold onto this UV curable resist. So again, the substrate is PET. Then you do the roller imprint. So again, we use the roller again. This is for the commercial application. We do the roller imprint to roll the mold. You make sure you have good contact between the mold and the substrate. You do the roller print. Then you shine the light. You get the pattern here. Then you put the silver ink nanoparticles, silver nanoparticles. Then you do the scraper. This is the same idea if you install the ceramic tile. When you install the ceramic tile, you use this similar process to apply the gluten. So then you have the silver ink filled into the trenches. Then you do the sintering process. When you do the sintering process, the silver nanoparticles will come together to form a silver metal. This one is commercialized by the company called SVG. This is a company in China. So there is also a US company working for the same idea, but later on this company got bankrupted. For the Chinese company, this one is a big company, so they have lots of money to work on this product. Take this company 8 years to develop this product, Take a long time, even though it looks simple. But this is also from this for the cell phone microstructure by the UV printing lithography for the cell phone backside. So nowadays, since 2 years ago, you can buy the cell phone with this kind of very fancy backside. So how to make the fancy backside? Well, this fancy structure is made of the microstructure. So normally the structure size is 10 of micrometer. You have different, very different designs. You see all kinds of designs. You do some fancy design, then you can have this kind of structure. So how to make the structure? So after you have the design, you do the UV Curing imprint. This is done by the UV Curing imprint. But to have it more shiny, it is possible to coat hard dielectric film. So you may coat the hard dielectric film on top of the UV Curing resist polymer. So we use a soft plastic mold. So this mold is copied from a silicon mold. The silicon mold is also made. This company make the mold. Then they make many copy of the mold onto the plastic mold, and very thick UV resist. You do not do semi coating. You just paste resist onto the wafer. Then you roll. You put the mold onto the wafer. Then you peel it off. You shine the light. You peel off. It's very simple. When you need no or low pressure, so because the mold will wet the resist, so the resist will come to the mold by the capillary force. So low pressure, room temperature, you put the resist, then you put the mold onto it, you shine the light, then you peel it off. It looks a very simple process. But this process is done by manually. I have visited a company that makes this kind of product. They do this thing by manual UV imprint. They don't call it UV imprint. They do not call it UV imprint, but they call it UV embossing. But we know that we know about hot embossing. So here is the UV embossing. Because we use very thick UV resist. We do not do semi-coating. We just apply the resist onto the backside. So at the present, this kind of phone you can buy from from the Huawei Chinese phone. iPhone don't have this kind of things because iPhone wants to make it much better than this. This is another application called a diffractive security element. So you can see, so we have the grating. We have the grating structures, periodic line arrays. You get it colorful. This from the butterfly. Grating give you the color. Then we can make similar grating structures. It will also be very colorful. But this process can be done using the row-to-row nanoimprint. This one is done by this method, row-to-row. It's very cheap. You make many rows at the same time. Very low cost way to make the nanostructures. So we are shining the white light. So in the environment, so we have the white light. We have the white light shining on the grating. Or you will look at it from the side, you will see a color. You will see the color. So what color you will see? This color, the wavelength is given by page sin theta. So by far, I'm sure you are already familiar with this kind of calculation. So lambda over a p sin theta. So the same idea to what we see for the chapter 1 or chapter 2. So at the moment, this one is the largest commercial application. This one has the largest commercial application. Because this is easier to make. It's put on a credit card, a banknote, and also I know some company put this one on the chocolate. Other companies they put this thing onto the bottle of the wine. Some wine is very expensive to put this kind of security element onto the wine or chocolate and all kinds of things. So this is another example of the nanoimprint lithography application. So you make the large area greetings. So the channel width here should be less than 50 nanometer. And when the channel width is less than 50 nanometer, you flow the DNA through the channel. Then the DNA will be elongated. You can see the DNA will be stretched. So when the DNA will be stretched, you can see how fast it moves, how long it is, how fast it moves. This way you can get some information for the DNA. Then this can be used for the disease detection, DNA detection. So this is the idea. This is the idea for the company called Bio-Nanogenomics. So this is the company, Bio-Nanogenomics. But this company is also a startup company, spin-off from Princeton University. My Princeton colleague, so he started the company, and this company was founded in year 2000 and became IPO to Nasdaq IPO 2 or 3 years ago. So the work here is not, at the beginning, another professor from Cornell University who did this kind of work, but the student in my colleague, he makes this one commercial application, not just publish some papers. So the last example is the bit pattern magnetic recording media. So what is the bit pattern recording media? You can see here. So normally nowadays, so what we use now is called a thin film media. Right now we are still using the thin film media. So we have the magnetic film. Then you have many domains, magnetic domains. So this one may be up, something like this. This will say 1 1 0 1 0 0 1. This is how the data is recorded in the magnetic hard drive. So the problem for this one, you can see. So first, the boundary is zigzag. The boundary is not smooth. You have the zigzag boundary. We have zigzag boundary because you have the green. So this defect determined by the green of the magnetic film. If we have smaller green, they have many more greens, then it will be smoother. But if the green, this word. So ideally, we need about 1,000 greens so that we can have the smooth transition. But when the green is too small, when the green is too small, it becomes paramagnetic. That means the thermal energy will be able to switch it. This is not good. But to solve this problem, we can do this kind of, it's called bit pattern magnetic recording media. You can see each of the pillars is just one green. So this is one green. This is another green. This way you have very big green size. This is 1 and this is 0. And also the top. This one. If we have parallel here, they try to flip over each other. But when they are separated, they will not flip over. It will be more difficult for this one to flip over. This one to flip over this one. So from here, if you know about this, those two, and this is the low energy state. One up, one down. This is the low energy state. So these two, both the up. This is the high energy state. So this one is not so stable. One of them will try to flip over the other one. This one obviously give you a much higher recording density. And also you have the smooth transition between the different bits, and also all or nothing writing process. And also you can do the tracking. When you do the imprint, you can put the tracking patterns onto the disk. It's very good. So this idea was proposed in the early 1990s. But then, people ask the professor, my supervisor, ask him, so this looks very good, so how to produce it? Then he come out with the idea of the imprint, the nanoimprint. This nanoimprint is ideally fitted to make the pattern media. So that's why you can see For the case of 1 terabit per square inch, we need 25 nanometer by 25 nanometer. If each bit is 25 by 25 nanometer, this corresponds to 1 terabit per square inch. No other lithography can make large area dense patterns with 25 nanometer pitch. So the imprint will be the best way to make it. But this one, the company like Seagate, Western Digital, they have put a lot of effort to make the bit pattern recording media, but eventually it gave up in 2016. After this gave up, the company molecular imprint got bankrupted because they can no longer sell the mass production imprint machines to the company like Seagate. So because the problem, even though imprint is a low cost process, there is a defect and other issues. Right now, at the moment, so the idea is to use called heat imprint, heat resistant recording media. Heat resistant. So how does this work? So we know that for this one, the problem is that each of the bits they're not stable. To make it a very stable point up, you can increase the coercivity. If we have very high coercivity, the pattern here, the domain here will be stable. But we have very high coercivity, it is stable, but it is difficult to write. When you do the writing, you need to flip it to the downward, right? When you do the writing process, you need to flip it. But we have very high coercivity, it's hard to flip. So what is done here, what is the industry do right now? They shine a laser here. So when you shine a laser beam, it will be heated up. When it is heated up, the coercivity will be reduced. We have a smaller coercivity by the heating, then it can be flipped over. Then the laser is only a short pulse, so that this short pulse will not damage it. There's the flip over, then the laser is off. This is very good, very smart idea. So the last slide is who invented nanoimprint lithography. So the Professor Chou, he invented the nanoimprint in 1995. The Grant Wilson from University of Texas Austin, he invented a UV Curie nanoimprint 2 or 3 years later. But recently, it was found that in the 1970s, the Japanese scientists, you see this paper here, the Japanese scientists, they have actually they have done a lot of imprinting work. So the Japanese have done the thermal imprint, the UV imprint, and the step flash. This is also UV. They have done, and they also do the PPMS molding. So they have done a lot of work. They have done a thermal UV, step and flash UV, PPMS molding. All the work was done in the 1970s by the Japanese people. Well, you know that the Japanese people, they are very low. They are not very good at advertisement. But they do it. They did the work. They file a patent in Japanese. Nobody know it. That's why, in 1995, the Professor Chou and the Grant Wilson, they reinvented nanoimprint lithography in the 1990s. And the similar example is the carbon nanotube and the graphene. So we know that the carbon nanotube was discovered in 1991 by Japanese scientists. A graphene, single-layer graphene, was discovered in 2004 by the British scientists. But in reality, it was found that the carbon nanotube was first discovered in 1952. A graphene was first discovered in 1962. But those people, when they first discovered carbon nanotube or graphene, this one is published in Russian. One is published in Russian, another one I forget. So you see, those people, they make the work, but they do not advertisement, so nobody knows their work. That's why it's reinvented. Thank you.